You've probably met parabolas before, but have you met their more general cousins, quadratic forms? Quadratic forms are going to give us a more formal way to represent vector lengths, helping us calculate statistics of interest. This is Chapter 3 in a video series on degrees of freedom from statistics. In Chapter 1, we discovered a geometric way to represent statistical situations as random vectors, and we learned that degrees of freedom represents the number of dimensions a given vector can land in across samples. In Chapter 2, we talked about lengths and angles of these vectors. We saw how least squares can lead to right triangles, and then the Pythagorean theorem can explain the n-1 in the sample variance. But we also previewed in Chapter 1 that we're working towards a different definition of degrees of freedom, as the rank of the projection matrix in the quadratic form of a statistic. We'll start unpacking that in this chapter on quadratic forms. These are expressions that will help us get more algebraic with vector lengths, and since a number of key statistics turn out to be all about vector length, that means these quadratic forms will help us represent statistics of interest. The goal then here is to formalize the geometric intuition we've been building thus far. Here's our agenda. We'll first learn about quadratic forms in the abstract. Then we'll see how to represent quadratic forms using matrix multiplication. Finally, we'll figure out the specific matrix representation for the statistic we've been focusing on so far, the sample variance. Quadratic forms are algebraic expressions where we have the sum of multiple variables, but each term in the sum is of degree 2. That means it's either squared, like x squared, or it's the product of two of the variables, like x times y. An example might be x squared plus x times y plus y squared. We're also allowed to multiply each term by some constant, so another example might be 3x squared plus 2xy plus 4y squared. Okay, that's all well and good, but I think to wrap your head around quadratic forms, it's best to consider what these things look like. Let's do this. We'll take x and y to be our variables, and we'll plot the graph of a quadratic form into the third dimension z. Let's start with just the graph of z equals x squared. We can see the familiar shape of the parabola that we learned about in algebra class, but because we're in 3D, it also extends in a kind of cylindrical way, as if instead of making a parabola by folding a string, we made a parabola by folding a whole sheet of paper down the middle. Appropriately, this shape gets called a parabolic cylinder. If we put some constant in front to give us z equals ax squared, that number is going to scale the shape, where greater numbers make the parabola steeper, smaller numbers make it shallower, 0 turns it into a flat sheet, and negative numbers make it bend in the opposite direction. By symmetry, this should look the same if we replace the x with a y, and so look at the graph of z equals by squared, except that it's rotated 90 degrees. So what do you think we'll get if we add these two terms? Let's start with both the constants equal to 1. Well, if now we have to go parabolic along both the x and y axes, we'll get this kind of circular parabola or bowl shape which does just that. We call this shape a paraboloid. We're looking at a bowl that's circular, and that gets called a circular paraboloid, but if we start changing each of the constants, we can get steeper or shallower in each direction, and so giving us this asymmetrical figure, which is called an elliptic paraboloid. And because its cross-sections are elliptical, we can talk about ellipse things, like a major and minor axis. What happens if one of the constants goes negative? That means we have an upward opening parabola along one of the axes, but a downward opening parabola along the other, which combine to give us this saddle shape that's called a hyperbolic paraboloid. There's actually another way to get one of these saddle-shaped paraboloids, by plotting z equals x times y. How can we understand why we're getting this shape? Let's focus on the line that cuts 45 degrees through the xy plane, the usual line y equals x. On that line, since both coordinates have the same value, multiplying them together is the same as squaring them, so we just get an upward opening parabola. If we now consider the line in the xy plane that's 90 degrees rotated from this one, which would be the y equals minus x line, we get the same thing but with a minus sign, giving a downward opening parabola. Combining those gives us this hyperbolic paraboloid, just like before, except rotated 45 degrees from the x and y axes. Although I'm skipping the proof, it turns out that these are the only possible shapes we can make in 3D by combining variables in this way. Therefore, if we add together two or more of these shapes, we're always going to get another one back. And because of the cross term, the shape might not always neatly align with the coordinate axes. However, there's always some rotation we can do to the axes that will align the coordinate axes with the quadratic shape. We'll return to that in a later chapter. Hopefully that gives you a little more intuition about these objects. Now that we've seen how they're represented on graphs, we're going to consider how to represent quadratic forms with matrices. So we might want a quick review of matrix multiplication, including the dot product. I'm going to do that for the next 4 minutes or so, but you can skip ahead if you're comfortable with this already. We'll start with the dot product of a vector with itself. First, take 2 copies of some vector. Then we'll transpose the first copy, which means to flip it from being a column to a row or vice versa. Now we'll multiply each corresponding component and add them up. So we'll take the first elements and multiply them, then the second elements, then the third, and so on, and add all those up. This gives us the sum of squared components, which is exactly how we define the squared length of a vector in Chapter 2. So the dot product of a vector with itself just gives the squared length of that vector. If the vector is called A, we can notate this as A dot A, and also as A transpose times A. What if you take a dot product of 2 different vectors? You can do this same game, where you multiply corresponding components and add. Amazingly, it turns out that this result happens to equal the lengths of each vector times the cosine of the angle between them. This is rightly pretty mysterious if you haven't seen it before, and I won't prove it here, but you can find lots of coverage of this elsewhere. What I will say is that these dot products are pretty useful, especially for showing that 2 vectors are perpendicular. If the 2 vectors are perpendicular, then their dot product will be 0, because cosine of 90 degrees is 0. If you want a little practice with this, in the previous chapter we proved that the sample mean vector x bar is perpendicular to the residual vector x minus x bar. Our proof involved least squares and the Pythagorean theorem, but you can also prove it using the dot product, by showing that these 2 vectors always have a dot product of 0 and so must be perpendicular. I'll leave that as an exercise for the reader. Anyway, matrix multiplication is based on these dot products. A matrix is like a block of numbers arranged into rows and columns. To multiply 2 matrices, what you do is read across a row of the first matrix, at the same time that you read down a column of the second matrix, and do a dot product with these values. That gives you the entry at the first row and first column of the resulting matrix. If we move down a row in the first matrix and repeat the process, that gives us the value for the second row and first column of our result. And so on for the other entries. In this video, we're just going to treat matrix multiplication as a mostly algebraic operation, which will help us shorten groups of sums that otherwise would take up a lot of space. But in the next video, we'll give a little more geometric meaning to matrix multiplication as a linear transformation. Anyway, you might notice that for this to work, the rows of the first matrix have to have the same number of elements as the columns in the second matrix. We're allowed to have different size matrices, but if they don't have this characteristic, then you can't do standard matrix multiplication on them. Finally, just like how multiplying by 1 leaves a number unchanged, there's a matrix you can multiply by which leaves a matrix unchanged. This is called the identity matrix, and it has a 1 on every diagonal element and zeros elsewhere. I'll leave it as an exercise to the reader to try this to see that it really works. Anyway, the identity matrix usually gets given the name I. Okay, review over. So how can we represent quadratic forms with matrices? Let's go back to our quadratic form and start with a little renaming. Instead of coordinates x and y, let's call them x1 and x2. That's just aesthetic, but it allows us to follow the usual convention of collecting these into a column vector and naming the whole vector x. We saw that a vector dotted with itself, which we can also write as x transpose times x, gives us the sum of squares, which is the squared length of a vector. This is a quadratic form. So we're seeing that we can represent a quadratic form as a matrix product. Or at least this one quadratic form. We don't yet have enough machinery to represent any quadratic form. For that, we'll need to add an additional matrix to the product. For now, I'll call that matrix A, and the product we get looks like this: x transpose times A times x. Okay, what is this matrix A doing? For reasons that will become clear in a moment, I'm going to give the entries in A names that look like this. I'm calling the diagonal elements A and B, and I'm calling the off-diagonal elements C1 and C2. Okay, so the full product of our 2D quadratic form with all of the entries looks like this. Next, let's multiply this out the long way, starting with A times x. Then we'll multiply by the row vector x transpose in front. Distributing and simplifying, we get this. Hey, would you look at that? We've got an x1 squared term, an x2 squared term, and an x1 times x2 term. And in front of each term is a constant that comes from the values in our A matrix. So, by choosing those A matrix entries, now we can represent any quadratic form using this notation. There is something interesting going on with the cross term, though. The actual coefficient on it only depends on the sum of the off-diagonal elements, C1 plus C2, but it does not depend on the exact values we pick for C1 or C2. We could put different numbers in the off-diagonal slots, but as long as they add up to the same thing, we'll get the same quadratic form. For example, take these two different matrices here. The off-diagonal elements are different, but they add to the same thing, both a 6 here, and the diagonal elements are the same. So if we look at the full quadratic forms each of these matrices produce, we'll find that they're the same, with a 6 for the cross-term coefficient. Different matrix, same quadratic form. Because multiple matrices produce the same quadratic form, that gives us some freedom to just pick one of them and run with it. So which should we pick? What we'll generally do here is make the nicest choice we can, which will be to split the cross-term coefficient just directly in half. In our example, that looks like this, where we use two 3s in the matrix, which add to our coefficient of 6. The reason that's nice is because it gives us a matrix that is symmetric, meaning the matrix is mirrored across its diagonal, so that if we were to take its transpose, to flip its rows and columns, we just get the same matrix back. Symmetric matrices have some nice properties, which we'll talk about more in Chapter 4. Finally, I'll note that all of this applies beyond just 2 dimensions. We can make a quadratic form of degree 2 terms, now from the variables x1, x2, x3, and so on. We can express any quadratic form as a matrix product of x transpose times a matrix times x. And for the off-diagonal elements in that matrix, only their sums matter, so we're free to choose a symmetric matrix to represent our quadratic form. It's a lot harder to picture what these look like in higher dimensions, but conceptually, we're adding parabolas in more directions. Now that we understand how quadratic forms can be expressed with matrix multiplication, let's now figure out how to express the vector lengths that we care about as quadratic forms. Again, this matters because many statistics of interest closely correspond to these vector lengths. Let's return yet again to our geometric setup from prior chapters, where we are drawing n random numbers represented as a data vector x. The draws are independent and identically distributed from a distribution with mean mu, which we represent as a vector like this. We can also take the sample mean x bar. Finally, we'll consider deviations of the data from these means. For mu, we have the error vector x minus mu, and for x bar, we have the residual vector x minus x bar. See the previous chapters if you need a refresher on this diagram. So again, what we're about to do here is express the lengths of these vectors algebraically using quadratic forms. Now, in one sense, this is very simple. We know we get a vector length by taking the dot product of the vector with itself, so we can just do that for all of the vectors. For example, if we want the length of the data vector, that's x transpose times x. If we want the length of the sample mean vector, that's x bar transpose times x bar, and so on for the rest of them. And each of these gives us a sum of squares. However, the sum of squares it gives us is in terms of that particular vector. For example, for the residual vector, this would give us a sum of squared residuals. What's generally more useful is to try to write these as functions of the underlying data. Specifically, since x bar is a function of x, both the sample mean and the residual vectors can be written in terms of x. So we want to simplify these quadratic forms a bit, because that'll show us how to get from the data directly to the statistic of interest. Now, the statistic we've been the most interested in so far is the sample variance. In the previous chapter, we showed that the sample variance is the squared length per degree of freedom of the residual vector, and that its expected value is the variance of the underlying distribution, making it an unbiased estimator of the population variance. Since this is based on a vector length, it can be written as a quadratic form, and we want to write it in terms of x directly. Now, if we have a small number of observations, like say n equals 2, we can go directly from the sample variance to the quadratic form by expanding the sum, substituting in the mean, collecting like terms, multiplying out the squares and collecting terms again, and reading off the coefficients. For n equals 2, this method isn't so bad, but for larger sample sizes, it quickly becomes a complete mess. Fortunately, there's another method we can use to find the quadratic form, which will actually be more insightful. Before we do that, though, let's look at the graph of this thing. The xy plane on this graph shows all possible values for our two data points, and the red surface shows what the sample variance would be for each possibility. Notice that it's a parabolic cylinder, but it's not one that's lined up with the coordinate axes. Looking at the graph, the flat section of this graph, the fold line if you like, is actually along the line y equals x, which is where x1 is equal to x2. What does that mean? Remember that this is the variance, which measures the spread in the data. Along this line, the two data points are equal, so there is no spread, so we just get 0. The farther we are from this line, the bigger is the gap between x1 and x2, so we get a bigger spread and so a bigger sample variance. Okay, now let's see how to find the quadratic form for the sample variance for the more general case of larger sample sizes. In Chapter 2, we showed that the residual vector will be perpendicular to the mean vectors, giving us a right triangle. And right triangles let us use the Pythagorean theorem. This gives us that the squared length of the residual vector is equal to the squared length of the data vector minus the squared length of the sample mean vector. Let's focus on that first term on the right. We saw earlier how to represent this as a quadratic form. It's just x transpose x. That gives us the sum of squares of each of our data points, which in our two-dimensional example looks like this. To make this line up with our notation earlier, where we had a matrix in the middle, let's add in the identity matrix. This is like multiplying by 1. It doesn't change the value, so we're free to do it, and it'll come in handy later. If we turn to the graph of this thing, we see a circular paraboloid. Because it's the sum of squares of the data points, it's only 0 when both data points are 0. Back to our formula, let's now turn to the second term for the sample mean. If we can represent the squared length of the sample mean vector as a quadratic form in terms of x, then this difference would give us the quadratic form for the residual vector. Expanding it out, each component of the mean vector is just the mean, so its squared length is just the sum of a bunch of squares of the mean. So that's what we're looking to express, but we want to do it as a quadratic form using the observations. To do that, we have to know how to write the mean using matrix notation. In other words, we're going to try to find some matrix expression that involves an x, which spits out the sample mean vector. If you like a puzzle, this would be a good time to pause the video and see if you can figure this out. The first step is that we multiply our data vector by another vector that's just made up of 1 over n for every component. That looks like this, and the result we get is just the mean as a single number. But we want a vector, not just a number, so the next step is to get a vector that has this for every component. For that, we can just multiply this scalar by a vector of all ones. This gives us the result that we want, but we're not quite done simplifying. Being a little tricky with the order, let's actually multiply out these two vectors first. This results in a square matrix with 1 over n in every position. If we factor out the 1 over n, we're left with a matrix of all ones, which often goes by the name of J. So condensing this down, we have an expression looking like this. Our sample mean vector is j over n times our data vector, where j is a matrix of all ones. The thing we're looking for is the squared length of this vector, which we can get by dotting this with itself, which as usual involves taking the transpose of the first item. The transpose distributes through and reverses the order, so we end up with this expression here, which involves j transpose multiplied by j. J is a symmetric matrix, so taking the transpose just leaves us where we started with a matrix of all ones. In other words, j transpose is just equal to j. So what do we get when we multiply this out? To see that, let's just consider multiplying a single row and column of ones, like this. This ends up being just the sum of n ones, so the result is n. So back to j times j, we'll be doing that same procedure for every entry, so we'll just get a matrix full of n's. We can then factor that back into n times j. So we've just figured out that j transpose j equals n times j. Back in our quadratic form, substituting that in, our final result for the squared length of the sample mean vector comes to x transpose times j over n times x. To make it a little more concrete, let's consider the 2D case, where j over n would give us this quadratic form. If we take a look at the graph of this, we again get a parabolic cylinder, but now the fold lines up with the y equals minus x line, meaning we get 0 when our second data point, x2, is the negative of our first data point, x1. So what's going on there? If our two data points are negatives of each other, then the sample mean is just going to be 0. So the squared length of the mean vector will be 0 as well. While we're here, since we've seen each part of the formula separately, let's look at them together. What our Pythagorean theorem formula is telling us is that the two parabolic cylinders, the blue and the red surfaces, add up to the circular paraboloid, the green surface. That was a lot to get lost in, so let's zoom back out to review what we're doing here. We're saying that certain statistics can be represented as quadratic forms, and we're trying to find the representation for the sample variance, which is the same as the squared length per degree of freedom of the residual vector. We've established that by the Pythagorean theorem, its squared length is the squared length of our data vector minus the squared length of the sample mean vector. After some painful manipulations, we now know that you can represent the squared length of the mean vector as x transpose times j over n times x. Throw back in that the squared length of the data vector is x transpose times the identity matrix times x, and this lets us factor in the way that you might think. And so our result for the residual vector looks like this: x transpose times I minus j over n times x. This is the quadratic form representation for the squared length of the residual vector. And this part in the middle, the I minus j over n, is the matrix for the quadratic form. And again, dividing this value by n minus 1, which are the degrees of freedom for the residual vector, will give us back the sample variance for our data. Okay, so we've learned about quadratic forms and worked out the quadratic form representation for the sample variance. In the next chapter, we're going to look more closely at the matrices in these quadratic forms. It turns out these matrices have some special properties because they are projection matrices. Then we'll complete the definition for degrees of freedom that we're working towards, as the rank of the projection matrix in the quadratic form of a statistic. See you then!